Good morning, good afternoon, or good evening from wherever you're viewing this webcast. Welcome to the Fibre Channel Industry Association webinar, live webcast, Fibre Channel Data Center Interconnects. I'm your host and moderator, David Rodgers. I am the board member for the FCIA, working on events and such as one we're presenting here. I'm also a business development manager for EXFO. Our guest speakers today from Adtran, Mr. Gene Cannella is the principal systems architect, will be leading today's discussion. Andy Adams, who's the PLM for the group and director of that group, will be here for support and mostly questions on the follow-up. So we'll be hearing a lot of Gene, some of me, and hopefully some of Andy when we get down to a Q&A session. I point out Q&A at any time. If our audience has questions, please don't hesitate to post them into the questions block. And if they're germane to the immediate topic, we might answer them immediately. Typically, we wait till the end and have a Q&A session at the end. But anytime you have questions, please don't hesitate to add them in. The FCIA, the Fibre Channel Industry Association, is the mutual benefit, nonprofit, international organization of manufacturers, systems integrators, developers, vendors, industry professionals, and end users. I point that out because it's a clearinghouse for the information that is pertinent to Fibre Channel, whether that's coming from the engineering community or whatnot. Fibre Channel Industry Association is the voice of Fibre Channel for the world at large. We have 25 years plus of promoting Fibre Channel technology, from 1 gig back in the day, well, actually, but before that, but 1 gig back in the day, to where we are at 64 gigabits per second frame travel in per lane. It's amazing that we've come so far. We do host the industry leading members of the Fibre Channel community, and we're very blessed to be able to do that for people. And shipped since 2001. This is one of my friend Mark Jones' favorite stats. 160 million Fibre Channel ports have been shipped since 200. I think that's a little bit low. I think we're above, we're getting closer to 200 million at this point, but that's still a sizable number of secure storage ports available in the world. At this point, I'm going to hand it over to Gene, who's going to take us through the agenda and give us some real meat and potatoes here. So Gene, take it away.
Thanks, David. Hi, everyone. Gene Cannella. Our agenda today, we talk about data center interconnect, all the reasons we might do that and how we might do it. And we're particularly interested in extending Fibre Channel. There's a lot of other signals in the data center that need extension, that need interconnection. I lost a slide. Okay, it's back. So we'll mention that. We all work in a converged world with a lot of IP, a lot of Ethernet. So we'll talk about that and why we do it, and the different types of interconnect, how we can extend the fabric, the technologies that enable it, DWDM, OTN, cryptography. And when you're extending the SAN fabric with DWDM, 100 kilometers or so, buffer credits become something to be thinking about, and we'll have a good discussion on of buffer credits. And if we're interested how my Fibre Channel signal survives this transport distance and how I can tell where it's going, where it's been, what its health is, supervision, we'll talk about those things. So off we go. So show here a few data centers. They're connected in no particular topology. Some have connection to more than one data center. Some only have a peer data center. Fibre Channel has been fantastically successful in the data center. With the Fibre Channel, you create a storage area network, and what that does for you is lets you separately and independently scale the compute and storage. So the SAN fabric that's letting you do that also integrates with a LAN and IP-based applications, switched and routed networks in the data center. And we need to scale all of those. We need to make sure they're available all the time. We need to make sure they're secure and survive 21st century kinds of events that might want to try to take our data center down. And we want our resources redundant and available, applications and data replicated. And if we can do networked interconnection of data centers, we can improve all those dimensions of performance. So what kind of things are we doing when we connect the data center? Well, the first people became interested in business continuity and disaster recovery. If a data center catches fire or loses power and the generators run out of gasoline, I don't know, and I hesitate to wish anything into existence by naming the kinds of disasters that might happen to a data center. So we make plans for continuity of operations and recovering from the disasters, whatever those disasters are. And there's a little note down there to explain the nuances between business continuity planning and disaster recovery planning. People often think of them as the same. There's a little difference. But once we started interconnecting data centers, we discovered we could do workload balancing and create mobility of the workload, mobility of the active machine, whether it's physical or virtual, and more efficiently use all these resources at scale by using them across all the data centers that we can. We can share resources, we can scale. And if we're doing those things, we need to make data exchange, we need to do data replication. And another application is data center migration. An organization might outgrow a facility it's in, or they just may be migrating applications or a slice of their fabric. So there's methods for migration, and you need the data centers interconnected to do that. So what kind of connectivity does data center interconnect need? Three basic kinds. And everyone in the world has an IP routed network. Your data center is going to have internet service or leased IP routed resources. And you have IP applications that tolerate the latency of an IP routed network, that tolerate the non-deterministic latency of the IP routed network. And those applications can run without the DWDM network. You just lease a connection to the WAN. Mention that Fibre Channel over TCP/IP, or what we call FCIP, exists here. It is a protocol that lets us tunnel Fibre Channel operations through IP networks. And you can use that for some synchronous operations, but mostly that's used for asynchronous operations. It has global reach. If you can afford to do things asynchronously, your replication asynchronously, you can use FCIP. So being interested in Fibre Channel, here's an example of why we don't ignore the layer 3 extension. Layer 2 LAN extension extends a single layer 2 domain across data centers. Here, I'm creating a virtual Ethernet fabric that exists across these two data centers, and that enables a distribution of physical resources, facilitates mobility of the active machine, as I mentioned earlier. You might need to extend the LAN in order to interconnect high availability clusters. Their connections, their protocols they run may not operate successfully over a layer 3 routed network. So you look to extend your layer 2 LAN. Interestingly, for the layer 2 LAN extension from one data center to another, the Ethernet can take the DWDM path we see offered here, or can use layer 2 tunneling technologies through the WAN. And Fibre Channel over Ethernet exists there. I can't speak to the popularity or adoption of Fibre Channel over Ethernet, but if you did want to do that, that's where it would be. But what we're really going to talk a lot about today is the SAN extension, the Fibre Channel extension. Here we're going to remote a partition of the fabric, and we'll interconnect these data centers with ISLs, interswitch links, so that the fabric in one data center is part of the fabric in another data center. Lets us extend it and scale it across these facilities. Lets us use native Fibre Channel methods to do the replications we want, the synchronous transactions, out to a distance for which the latency is tolerated by the application. And that might be 2 or 3 milliseconds. But up to that distance, if you go over this DWDM network and you extend your ISLs from data center to data center, you can extend the fabric and you can still do synchronous transactions between data centers. So as I mentioned at layer 3, FCIP, layer 2, FCOE, Fibre Channel SAN extension, we're extending ISLs. So let's jump on. What's the technology for doing that? Two enabling technologies for the physical transport. Dense wave division multiplexing, DWDM, that's simply a way of optically combining multiple signals onto one fiber. Each signal occupied one tunable or tuned optical channel, and there's optics technology for combining them and separating them back out at the other end. And this technology scales to over 100 wavelengths. So whatever bandwidth you can put on one laser on one wavelength, you can combine it with 100 others and get all that bandwidth through this optical line. The digital complement to DWDM for these applications is the Optical Transport Network, which is an ITU standard for providing a low overhead, low latency system that'll let you supervise all the wavelengths on the DWDM, and it lets you supervise all the client services. So all of our Fibre Channel and maybe some Ethernet, each one of those links gets transparently mapped into an OTN carrier and then multiplexed onto the DWDM system. So this digital mapping, very thin overhead, some bandwidth dedicated to forward error correction, you can scale that from as low as 2.5 gigabits per second to multiple times 100 gigabits per second. And today we see 400 gigabits, very common, and 800 gigabits per second emerging. And again, that is per wavelength before you then put 100 wavelengths on the fiber. So that is the physical transport we're going to use to extend the ISLs between the fabrics in two data centers. As I've kind of already mentioned, when we're using DWDM with OTN to extend the fabric, it's typically nearly universally used to transport ISLs. This remotes the associated E-ports. The E-port on the link in this data center is talking to an E-port at the other end of the link in another data center, 80 kilometers away, 100 kilometers away. They've been remoted, but they're still part of the same fabric. It's generally not a good practice to try to remote F ports or N ports that's an inflexible, difficult to scale way of doing it. So that creates a logical architecture for you that extends the SAN across the multiple data centers. And DWDM is the lasers and the optics. OTN is the digital mapping and multiplexing. So a couple of notes here. Best practice, if you want to efficiently use that DWDM, it's super high bandwidth. It's super high performance. It's a valuable asset. So you want to use it efficiently. Best practices to transport the ISLs in your data center that are running at the highest rate supported by the fabric. And today, as we've said, that rate is becoming 64 gig. So what we see our DWDM being used for now is to remote 64 gig ISLs. But of course, the lower rates like 32 and 16 are still supported on the DWDM system. I hope not. That I clicked the wrong button. As I said before, the DWDM system can support over 100 wavelengths per fiber. Each wavelength might give us 100, 200, 400 gigabits of payload, with 800 gigabits per wavelength now merging. So you take these multi-hundred gigabits per wavelength, you put 100 wavelengths on a fiber, and that one fiber in the DWDM system can give us 10 to 80 terabits per second. So it's going to give us plenty of bandwidth, and we just have to remember that if we're doing fiber channel, we're also probably sharing the fiber with Ethernet at another pardon me, wavelength. And how much 64 gig can I fit in these OTN chunks of bandwidth? Since OTN starts scaling from 2.5 gig, and once it hits 100, it gives you, each step of bandwidth is 100 gigabits per second after that. So 64 gig is more than half of 100, so it takes one up if that's all you have. So 100 gigabit per second OTN signal can carry one 64 gig fiber channel, but it has some bandwidth left over, and you can multiplex in a 32 gig with it and a 16 gig before you fill up the 100 gigabits per second. If you double your OTN line rate, you don't just double the 64 gigs you can handle. There was leftover bandwidth in the 100 gig and leftover bandwidth in the next 100 gig, and add those two pieces of residual bandwidth together, and you can fit a third 64 gig fiber channel with, again, a little leftover bandwidth for some lower rates. 400 gigabits per second, now we get even more efficient because I can carry 7. I'm starting to get to almost, and I'm never, of course, never going to get to almost 2 times 64 gig per 100 gigabits per second. That's the limit. 800 gig, it doubles, 14. So that gives you an idea of how the fiber channel scales with the scaling of the OTN. I've mentioned synchronous transactions, and what we see everywhere is that synchronous replication can be supported between multiple data centers at up to 100, 150 kilometer distances, as long as the system you're using to do that doesn't add a lot of latency beyond the time it takes light to travel that distance. So entering and exiting your transport network needs to have minimal latency so that it's just speed of light that you're worried about. And don't show it on the slide here, but you can make a rough approximation of this, how fast light travels in the fiber. creates 5 microseconds of latency per kilometer. So 100 kilometers is 500 microseconds. And a synchronous transaction, a SCSI write or an NVMe write, includes the necessity of traveling that distance 4 times. There's a command that must travel to the other end, and an acknowledgement of the command that must come back. Then the write or the data must travel back, and the acknowledgement must come back. So it's 4 trips across that fiber to complete that transaction. 4 times 500 microseconds is 2 milliseconds. So, and at 150 kilometers, that's 3 milliseconds. Now we're starting to test the limit of the synchronous applications. But up to those distances, you can expect to be able to support synchronous transactions. OTM and DWDM exhibit deterministic latency. It's not like a routed network where you don't know how much delay there will be buffering and routing. There's a very small latency getting onto the network, we call ingress. Very small latency getting out of the network, we call egress. For native fiber channel traffic, it's typically 5 to 25 microseconds end to end, and that includes the forward error correction. So you add that to the speed of light, and the result is ingress and egress of the DWDM network represents 1 to 5% of the latency contributed by the time it takes speed of light to travel that distance. So it's doing a good job of letting you take advantage of the distance that you need. That 5 microseconds of ingress egress represents 1 kilometer. And if you're 100 kilometers away, do you know how directly your fiber was routed? There's a lot of play in that. So 1 kilometer, it's not too significant a contribution. But
hey, Dean, I'm gonna run in here. We got a question I think is pertinent to the topic at hand, and it's one from our friends at IBM, talking about running into problems having to set fixed speeds on these on either an N port or an E port when attaching to their DWDM for extension. Do the current or the modern DWDM systems with OTN have the capability to auto negotiate the FC speeds now?
So what you see is the DWDM client port facing the fabric switch supporting auto negotiation, but only advertising one rate, only supporting one rate. If the switch can auto negotiate, but the rate list will only be one rate, then yes, they could auto negotiate, and it will be the only rate. But if it has to be configured for that rate, what you generally aren't seeing is the DWDM ports able to change rate on the basis of auto negotiation. You can see those ports be configured to different rates with the same hardware, same optics, same module can be provisioned for different rates, but they probably won't change rate based on auto negotiation. But they do support the protocol. I don't know if that helped.
Thank you, bud.
Okay. So the point I was going to make is we can support these synchronous transactions out to 100 kilometers, 2 milliseconds. But we're going to need a lot of buffer credits, whatever those are, because that's a long way. Brief diversion on DWDM again. As I said before, you fit many optical signals on the optical fiber or a pair for transmit and receive. The optical signal will occupy a channel, and the channel width is provisionable generally, but the channel spacings are standardized according to an ITU-defined grid. Center frequency spacings commonly range from 37.5 gigahertz to 150 gigahertz in increments of 6.25. So everyone knows where their wavelengths have to go. And what components do we need to build out the system? Well, the DWDM systems employ transponders and muxponders, which I've mentioned briefly before. Two purposes. First, these devices adapt the native client protocol, the fiber channel or the Ethernet, to the network transport protocol, which is OTN. It's a transparent adaptation and a very light overhead, but it's generalized. It doesn't try to be aware of or terminate frames, packets. It operates at the link layer and carries PCS characters. I'll talk about that a little bit more later. So that's the first purpose. A transponder or muxponder adapts the native protocol, the fiber channel, to the optical network protocol. The other important thing you get these devices is you retransmit the client optical signal with a tunable laser on a DWDM grid frequency with higher power and longer reach. So the optics within the data center are generally too wideband for DWDM, although they could be CWDM or even DWDM if they were to choose to pay for those, but generally they're not. And generally, because they only have to go tens of meters or hundreds of meters, but not kilometers, they're lower power and lower performance and lower cost. So now we want to go a long way. We need to retransmit that signal. And that's another thing that the transponder muxponder gives you. So see in the drawing here, 64 gig, 32 gig, 16 gig in the data center, hitting these transponders and muxponders and seeing them mapped into 100 or 400 gigabits per second and on a color, a particular wavelength. Now we always draw them Roy G. Biv, red and green and blue in these drawings, but in fact, they're all incredibly fine shades of infrared. They're all the same color and we can't see that color, but they're very, very slightly different. That's how that system works. The add drop multiplexer lets you combine those, the red and the green and the blue, onto one fiber, and they're separable because they're channelized. If you need to go a long way, you can amplify it. And here I show an amplifier, but at the 80 kilometer distance, you often don't need amplifiers. The laser in the transponder is easily powerful enough and clean enough, high performing, to reach that data center 80 kilometers away. So what drives the deployment of DWDM networks? We need to transport some Ethernet. We need to transport some fiber channel. But there's a lot of other protocols in the data center, and we may need to interconnect those as well. InfiniBand, Rocky, whatever. We don't care. We're thinking about fiber channel. But we coexist with these things. So OTN gives us a system that generalizes the way we adapt all these different client types, these traffic types, into the optical network that doesn't have to put a lot of effort into knowing it's Rocky, InfiniBand, fiber channel, Ethernet. It has a way, a general way of adapting those signals into the optical network. It's the first thing OTN does for us. Then once you do that and you do the DWDM, you've got tens of wavelengths or hundreds of wavelengths, and as many or more client services. At the bare minimum, there's one client service for every wavelength. If it's a transponder and that 64 gig fiber channel gets its own 100 gigabit per second wavelength, then it's 1-to-1. But if it's a muxponder, it's a 400 gigabit per second wavelength, and it's carrying 7 times 64 gig fiber channel. That's a big multiplier. So now we're starting to talk 1,000 client services, 1,000 fiber channels. We may not need that many between the data center, but that's a possibility. All this stuff needs managing, and OTN gives us a protocol, an infrastructure to manage the client services and the wavelengths carrying them. The overhead bytes that I showed in the previous drawing, or a couple drawings back, give us byte channels to do that. And here it is again. So this is the information containment structure for OTN. And what you see in the gray are 64 gig fiber channel frames. Well, to be fair, 64 gig fiber channel PCS characters are what's being mapped in there. The 64B, 66B, or transcoded. Anyway, the fiber channel is transparently in there. If you take off the overhead, you take off the FEC, you could read the fiber channel with a fiber channel device. But you put a little bit of overhead on it, and that gives you a set of bytes that are dedicated to different purposes of supervision, of knowing about the health of that link. And at the end of the structure, you put on forward error correction. We don't want retransmissions, so we want a very low bit error rate. With powerful forward error correction, you get corrected bit error rates that are not problematic for the client signal. Very rare to see an error because you fixed it with the FEC. And notice this little note here. It says independent encapsulation per ISL. As I said, these are fiber channel frames, but they're all from one ISL in this information structure. If you have another ISL, it will get its own structure that looks like this, and they'll be separately carried and separately managed. Another thing you're going to want when you go outside the building is encryption. So a DWDM system is going to provide you cryptography for security of your layer 1 traffic. Often there's no discussion about whether or not to do it because it's simply a requirement of the regulatory environment, or the customers of the data center services that may have their own regulatory constraints or liability they don't want to see, so they want to secure their data. So over the DWDM network, the fiber channel that has been transparently mapped is encrypted, and it's encrypted end to end on the DWDM, but that encryption comes off before it goes into the fabric. This is part of a layered security strategy. Defense in depth is what security experts talk about. Encryption at every layer that you can. Encrypt data in motion, encrypt data at rest. These ISLs between data centers are data in motion, and encrypting in motion complements any strategy you have for data at rest encryption. Doing this in DWDM, it's done the same way for all these protocols. These transparent mappings allow you to use the same encryption algorithm, same encryption approach, same encryption hardware, whether you're encrypting Ethernet or fiber channel. Systems leverage AES methods and integrate with public key infrastructure. AES 256 is what everybody does. It's built into your laptop. It's built into your mobile phone. It's built into every web page. That's well understood. And the difficult part of building the system is managing the cryptography, distributing the keys, authorizing the users. So a crypto management system is going to come along, and you see here distributing keys, and you see the encryption starting and stopping at the DWDM demarcs. We hear a lot about quantum computers are going to break public key cryptography, but quantum safe algorithms have been developed, and quantum safe key distribution is already available. So that's staying ahead of the rate at which quantum computers are developing. So now let's talk about buffer credits. That's always exciting when we are interconnecting data centers. And I, of course, can't know the audience familiarity with the buffer-to-buffer credit scheme basics. So 2 or 3 slides here just to hit that.
Gene, let me just bump you for a second. 2 things. One, we have a pertinent question right now, which was, does the FC SAN switch also need to support encryption if the DWDM transponder muxponder is configured for it?
I think that that's a choice. I think that you see a lot of users choosing to encrypt at multiple layers, or double encrypt at one layer using 2 different sets of keys, 2 different management systems in case one gets hacked, the other one's still secure. So you may choose to do it. I think that the reason the switches integrated encryption is the same reason the DWDM system did. So you could also choose to just use one of them.
But you can layer one atop the other, so that you
Absolutely.
can support, and in some of the implementations for Fibre Channel in government and financial high-speed trading, it's mandatory to have end-to-end encryption. So whether that's also being transported over a DWDM link, you would still have encryption from end to end, even without the DWDM. So, And as far as your buffer-to-buffer credit, I'm going to give a plug to the FCIA and the webinars. Barry Maskus has done, and several people have done a lot of specific webinars on buffer-to-buffer management and credits, how they apply. And if you really want to get nerdy with it, hit the FCIA website and look up some of the past webinars for buffer-to-buffer credits.
And there's a list of them at the end of, at least a subset of them at the end of this deck, and they're fantastic. I've looked at a lot of them, and they're really good.
Yeah, they are.
And I'm not going to try to go into it as deeply as they did.
I'll get out of your way now then.
Yeah. Okay. So let's imagine we're inside the data center and all of our links are short. If you have a short link, there's only one packet. There's only one frame in transit between the switch and the host at a time. The first bit of that frame arrives at its destination before the last bit gets transmitted. So you don't have to worry about frames in flight when you're on short links. So why do we have this link-based flow control? Well, it's trying to accommodate instantaneous short-term differences between the transmit rate of one device and the ability of the device at the other end not only to receive it, but to process it. The receiver may be oversubscribed. It may simply be bogging down doing something complicated. It may be receiving a lot of short frames. So it may not be able to keep up with the wire speed of the link. And it needs to slow down the transmitter when that happens so that frames don't get dropped. Frames get dropped, then sequences have to be retransmitted, and that's bad. So it's better to reduce link utilization, the efficiency at which you're getting bits across compared to wire speed. It's better to reduce that as long as you don't drop frames. So Fibre Channel has end-to-end flow control at higher levels of the protocol. We're not talking about that. It has link-based flow control just between two devices on a 64 gig Fibre Channel link, whether it's an ISL or a hosted fabric link. Every device can slow down the transmitter talking to it if it's falling behind. And the way, did I hear a question? The way it's done is using this notion of buffer to buffer credits, abbreviated BB underscore credits. But I'm going to call them buffer credits mostly because that's fewer syllables. In this scheme, a device can only transmit if it knows that the frame it's about to transmit won't overrun the resources of the device at the other end of the link. The buffer to buffer credits is an accounting scheme to let a transmitting device know how many frames it can transmit before it does overrun its partner, its link partner. How does that work? Super briefly. Starting from config time, a device will be configured, a port will be configured with a static number of buffer credits. This isn't going to change unless it's reconfigured. It's not going to change dynamically according to the protocol. You dedicate a certain number of buffers to this port. And every one of those credits is an indication the device has built-in memory resources to accept a frame and process that frame, one frame per credit. Doesn't matter how long the frame is, doesn't matter how many bits or bytes. Short frame takes a credit, long frame takes a credit. So if you provision a device with 10 buffer credits, that means it can accept 10 frames before it finishes processing the first one. And processing means if you're a host, for example, you move it up the Fibre Channel protocol stack. You move it up the stack to the application, and it's out of your buffers. If you're a switch, it may mean you've moved this frame to another port and transmitted it somewhere else in the fabric. But you need to finish processing and move this frame out of the buffer before you acknowledge that you've done so. So devices are configured. Then when the link starts up, they tell each other how many credits they've been configured with. E ports do this in the ELP, exchange link parameters. F ports do this in the fabric login. So now links started up. Each device knows how many credits the other guy has. And they're not going to continually tell each other that. They just tell them that one time. So each device has to locally keep a counter to keep track of how many frames have been transmitted, how many frames have been acknowledged. So you transmit a frame, your transmit buffer counter will tick up by one, increment by one when it transmits a frame. And it ticks back down when the frame is acknowledged. They get acknowledged with R-ready primitives. So the acknowledgement is not a frame, doesn't use up a buffer. It's just a primitive. And R-ready means receiver ready. And that says, I got that frame and I processed it. If over an intermediate to longer term period of time, you've transmitted more frames than you've gotten R-readies back, that transmit counter is going to keep ticking upwards until it hits the threshold of the BB credits number that it was told at the during ELP or floggy. And at that point, the transmitter has to stop. And that's the way that protocol works. So you see a device transmitting frames. You see its partner acknowledging that with our readies. If you really study this drawing offline after this is all over, you'll see I'm only showing one direction. So the frames are all going on any one link, one direction. The R-readies are coming back in the other direction. There is, of course, traffic in the other direction that would make the drawing too complicated. So please understand that when you study the drawing. But frames go one way, R-readies come back the other way. Every frame should be acknowledged with a receiver ready. Frames don't have to wait for that R-ready if the transmit buffer counter hasn't reached the limit, the buffer credit limit. And as I already talked about, what's this about? Instantaneous difference in the processing time. So what does it look like? Something like this sometimes. Frames are going, and then the first one arrives and it gets processed and the acknowledgements come back. So the transmitter got ahead for a while, but eventually caught up. As long as you stay inside the building, it's just processing time you're worried about. But now let's remote the fabric. Let's put them in data centers that are 100 kilometers apart. Now these frames and our readies have to travel 100 kilometers on that fiber. There's a lot more of them. And what I'm trying to show here is lots and lots of frames on the fiber. How many? We'll do some math in a minute to find out. There have to be enough buffer credits for as many frames that can be transmitted in the time it takes light to make the round trip. Because in one direction, the fiber will be filled with frames. And then in the other direction, the transmitters are waiting for the R-readies to come back, and it takes them just as long as it did to transmit the frames. So he'll transmit another double number of frames before the first R-ready comes back. So how many frames can you transmit in the round trip time? That's how many buffer credits you need. So if you're inside the data center, maybe you needed 10, maybe you needed 64. Now you need 10 or 64 plus a couple thousand. And here, let's do some math. 64 gig fiber channel example. What do we know? Given we know the speed of light, we know the index of refraction of the fiber. I'm wildly rounding off to make the math easy. And you end up with 2 times 10 to the 8 meter per second. We know the 64 gig fiber channel bit rate is 57.8 gigabits per second. The thing we don't know is how big are the frames. As I mentioned before, a buffer credit is associated with a frame no matter how small, no matter how big. So if you have big frames, they take up a lot of time to transmit. They take up a lot of distance on the fiber from the first bit to the last bit, and you need fewer credits. If you have a lot of short frames, you need more credits. So in our example, we're going to assume 100 kilometers to make it easy, 2,000 bytes per frame to make it easy, and we calculate what's a transmission time for a 2,000 byte frame. Works out to be 277 nanoseconds. What's the length? It's a little bit hard to wrap your head around. That frame is in transit, and the first bit is on the fiber, and the second bit is on the fiber 55 meters away, trailing it. But that's how fast light is and how fast we're transmitting. So you can envision a length of the frame on the fiber, and for 64 gig fiber channel, that's 55 meters. You need twice that many buffer credits, twice the length, the distance of the link divided by the length of the frame. And for 64 gig fiber channel, 2,000 byte frames, 100 kilometer interconnect, 3,600 buffer credits. And if you have shorter frames, it's more, 4,000, 5,000, 6,000. And you don't know a priori how long those frames are going to be, but your switch vendor has provided a user interface with statistics, and you can look back in time. You can look at average frame sizes, how many bytes you've transmitted, how many frames you've transmitted over time. It's a pretty good predictor of the future. You can use that to estimate your average frame size and do the math over again. What are some guidelines? Credits that you need are proportional to rate. If you go faster, you need more credits. 64 is twice as many credits as 32. It's proportional distance. 100 kilometers takes twice as many as 50 kilometers. They're inversely proportional to the average frame length. 2,000 byte frames require half as many credits as 1,000 byte frames. 1,000 byte frames eat them up. 800 byte frames eat them up. And you just have to make an estimate, and it's pretty useful prediction. And if it's not right, you can put in a bunch of extra ones if you have them in your switch pool. Or you can accept that the link won't be 100% utilized all the time. If you never run out of buffer credits, your link should be fully utilized. But you can't predict the transient behavior. So it's statistically unlikely that you can prevent it from never happening. So perhaps 99.9% is okay, or 99%. When the link stalls, there's no frame drops. That's the purpose of the flow control scheme. So no retransmission necessary. So it's not the end of the world to not get it exactly right, but you need to be in the ballpark. And you'll tell, again, the switch user interface will tell you how often you've stalled. I'm going to blow right past this. This is with OTN and DWDM. If you want to make sure your fiber channel is making it to the far end, you can put in a lot of different kinds of redundancy and protection strategies. You can protect the optical line, et cetera, and I'll give an example of line protection because that's very cost effective and very common. But OTN has inherited from the telecom industry the tradition of high availability, resilient, and protection. So as much as you want to pay for, you can get redundancy and protection switching. Line protection is simply in between the DWDM elements on that optical fiber that's carrying all those wavelengths. If you double the fiber, you can have a working path and a protection path, a path that will be available if the first one breaks, and you can switch between the two. And OTN gives you mechanisms for doing that automatically. So we don't have time to spend too much more on that. And finally, supervision. What does OTN give us? Performance monitoring. How many bit errors do I have at the OTN level? What are my forward error correction? How hard is it working? Has something gone wrong on a client port? Something gone wrong with my 64 gig fiber channel? Has something gone wrong with the network in between? We got fault monitoring, and we take consequent actions when there is a fault to repair the network or inform the customer prem equipment, the fabric switch, that the link has gone down. One of the ways we do that is error forwarding and maintenance signals. The DWDM system, the standard calls for if the link goes down and there's not really connectivity end to end for that ISL, the DWDM system itself will transmit NOS to tell you that what's this link, which you may or may not know has DWDM in the middle of it, is not operational, and hold off and start trying to do linking it over again, or shut down the laser, loss of signal, and follow the FCFS 5 steps when you see that. DWDM might also give you non-intrusive fiber channel layer monitoring as a value add. DWDM might look aside at the fiber channel as it goes by and give you performance metrics that the fabric port might have given you. How many, what's the error rate or whatever. Those things are all available in the DWDM. And summary, data center interconnect is table stakes and mission critical. It protects you against disaster, but it's also letting you scale. Layer 2, Layer 3, and SAN networks and applications using them all benefit from extending to a remote data center. And DWDM can extend the SAN fabric as far as 150 kilometers while supporting synchronous replication, but that uses hundreds or thousands of buffer credits, approximately 40 buffer credits per kilometer for 64 gig ISLs. 64 gig, in summary, is the latest and highest rate to be supported on DWDM and the fabric switches. If you don't have to go synchronous, because we're talking about data center interconnect, not just DWDM, you can use fiber channel over TCP/IP, FCIP, to tunnel your asynchronous transactions through the routed IP network and achieve global distances. And that is our story. We have 3 minutes for questions.
Outstanding. Thank you, Gene. One of the most immediate questions, and I appreciate the questions that came in. I know we answered a couple of them in line because I think they were more pertinent to the content that was going on. And you were just talking about what would happen if the signal went down. One of the questions was, what would happen if the fiber is cut, and how does the fabric recover? And of course, on that given link, you're talking about, hey, we're gonna retry this. But I think a lot of that would depend upon redundancies in your architecture, and if you had multiple routing capabilities or multiple ways to get from point A to point B.
Yes, a common scheme is the DWDM line is protected with redundant path, and if that fiber gets cut, the DWDM traffic might be restored in 50 milliseconds or 100 milliseconds. Something that shouldn't take the link down, although you probably empty out your buffer credits during that time.
Right.
But as long as it restores in less than a second or two, that's the timeout for link reset, buffer credit exhaustion. Your link probably doesn't have to do link reset or link init. And DWDM vendors try to differentiate with some clever things there, and we think we have clever things where we're not talking vendor specific. But yes, if the link goes down, standard says DWDM transmits NOS, and that tells the fabric, I need to do link init. You might do some other things, but yeah, you have redundant network usually to deal with that.
I had a clarification on the 100 to 150 kilometer distance. Is that a function of just the DWDM? Or, I mean, when we talk about subterranean or subsea transmissions, that's a hell of a lot more than 100 kilometers. But with repeaters and the proper transponders, effectively data centers are worldwide interconnected at this point anyway, right?
Yes, it's definitely not a limitation of the DWDM. The DWDM, like the IP network, can take you around the world.
Yeah.
With amplifiers, regenerators, submarine cable. The 150 kilometer limit is a limit on the round trip times for the synchronous applications, synchronous replication.
Okay.
Can't
Good
really tolerate any more latency than that.
Cool. One of the other questions that came in, and I know that you guys were doing some trunking in the past, which is what was the best practice for ISL trunking and DWDM? And that might be a webinar in and of itself.
That would be, and of course the main switch vendors have trunking features that are two different things. And I don't want to surmise which one we're talking about here, but
yeah, because they are different.
Yeah, and there's port channel, which is a similar thing, but what a DWDM system is going to want to do is minimize the latency, minimize the differential latency. So if you're doing link aggregation, which is what I think of as trunking,
Yep.
where multiple ISLs are logically one big pipe, you want to build your DWDM network so they all experience the same latency, whatever that latency is. If it's that 2 milliseconds we're talking about, we want it to be 2.0000 for each of them, not 2.1 for this guy and 1.9 for the other guy. So managing the differential latency is important. And then being transparent at the PCS character level, so all the primitives get through, because the mark primitive is important to that scheme, et cetera, et cetera. It's a whole webinar. It's a career.
Yeah, that's the main store. That's the main function of the primitives in the storage is quick communications without using up frames and other resources to make certain that you get the lowest latency and highest throughput. So. It's the trunking and the de-skewing of those data lanes. I mean, there's not a protocol out there, whether it's PCIe, USB, any of them, if they're multiple lanes, that maintaining differential timing and skew, if you will, so you can de-skew it, is super important. Last question I have on this particular sheet, and I think this is one that a lot of folks ask because of the advancements in storage protocols in the Ethernet space, but we have a question about why use FC interfaces rather than Ethernet interconnects. And do we expect FC to be replaced by Ethernet in the long run? And I sit in a unique position in our group here because I sit with both my feet in both camps. And I would say that the reason we still use FC interfaces as opposed to Ethernet is because of the inherent nature of Fibre Channel as a storage protocol. It is the preeminent storage interface. And when we think storage, I'm not talking about SIXL or NVMe per se. I'm talking about our traditional tape, our traditional rotating media storage solutions that have relied upon the robustness and the latencies and all the features that we've talked about with respect to Fibre Channel are built into FC directly. FC has only 6 classes of services, and only 2 or 3 of them are typically used in today's market. And it's been optimized over the course of the last 25 years to produce highest throughput, lowest latency, most effective transport for really critical data paths and in storage requirements, and predominantly you see it a lot in government, mil-aero, and high-speed trading and financial backplanes. One of the analogies I use in explaining it is that, like at the Schwab or the Fidelity brokerage house, you walk in and the customer service representative is on an Ethernet enabled PC, and they're doing their work, and they're talking to you, and they're executing changes, and then that goes to the router, which then executes that change or that change order, whatever, over the Fibre Channel storage fabric, because it is secure. And I have never heard of anybody having a intrusion over a Fibre Channel fabric. It's usually somebody getting an Ethernet email message, or somebody hacking in through a IoT device in a casino to gain access. But do I think Ethernet will be replacing Fibre Channel? No, I think Ethernet storage solutions will cohabitate with Fibre Channel, depending upon the nature of the traffic and the requirements for storing or securing that traffic in the fabric. We know that Ethernet is making a lot of advancements with respect to securing and providing a comparable experience, but I do not believe that Ethernet will fully replace Fibre Channel. They will cohabitate. And as a dear friend of mine once told me, he said every time he hears the phrase that Fibre Channel is dead and Ethernet is taking over, his bonus check got bigger. So anecdotal humor there, but I do expect that we will see a lot of Ethernet taking from Fibre Channel some of the goodness and trying to add it in to create a more robust solution. We see that today. I also know that NVMe over Fabric and NVMe in the Fibre Channel, or in the Ethernet space, will coexist for those same reasons, because now secure SSDs are being employed in a Fibre Channel SAN space to add, both speed and serviceability to the storage areas. So, I have a comment here. FC is never dead. I agree, sir. FC will never die. But no, I don't have any other questions on here. If Andy, if you would like to jump in, or Gene back in on any of those, I would appreciate it. Otherwise, we'll move into our closing slides. So as we asked at the beginning, please rate this event. We do want to get your feedback. We do want to know what you think about the content, and if you have any ideas for topics that you would like to see the Fibre Channel experts at the FCIA delve into even more. You can find our post and QA blog on the fibrechannel.org website, and the answers that we've talked about here will be included. This will be a on-demand webcast available in the library there. Is the bullet points here articulate? We have a lot of FC content on the on-demand webcasts. So, zoning basics, that kind of goes to what would happen if a link was cut. Do I have redundancy? Is that particular area zoned out? Lots of neat stuff is available on the website. And follow us at FCIA News on the socials for information about future webcasts. And on behalf of my colleagues and friends here at the Fibre Channel Industry Association, we do thank you very much for your time and participation. We know that you're taking an hour out, or in this case, an hour and 8 minutes out of your day. We really appreciate you. So thank you again.